Hey guys, welcome back to another video. This is going to be a new series where I'm going to try and complete the entire physical chemistry syllabus for A2 chemistry. Um, in this video, we're going to start off with chemical energetics, and there may be a few parts if I can't complete the entire topic in one video. So yeah, let's start off with enthalpy changes and chemical energetics in general. So first up, we have a definition, which is enthalpy change. We are already used to this keyword because we've learned about this in AS chemistry, where we knew about enthalpy change of formation and enthalpy change of atomization, along with others. So what does enthalpy change mean? It is basically the amount of energy transferred during a chemical reaction at a constant pressure. So what does this mean? The amount of energy transferred, meaning the energy may be lost in an exothermic reaction, or the energy may be gained in an endothermic reaction. So enthalpy change is the amount of energy transferred during a chemical reaction at a constant pressure. So what is the condition? A constant pressure. Why does that matter? Because depending on the pressure, the amount of intermolecular forces or the forces between the atoms or molecules are going to vary. And when the forces, or the stronger the bonds are, the weaker the bonds are affected, the amount of energy released will be affected as well, or gained will be affected as well, which is why the pressure is important. If there is greater amount of pressure, you will see greater attractive forces between the molecules, where for that reason, breaking those bonds or pulling them apart are going to be much harder, or forming those bonds are going to be much harder. So the enthalpy change depending on the pressure may vary, which is why the pressure should be a constant. So next we have enthalpy change of atomization. We denote it as del HAT. It is the enthalpy change when one mole of gaseous atoms is formed from its element under standard condition. So what are we doing? We're taking an element under standard conditions, let's say sodium atom, and then what are we doing? We're turning it into a gaseous atom. Being a gas is very important. So what is the change that is happening? We're turning it from a solid to a gas, and in doing so, this is the diagram. So let's say this sodium atom, it is a part of a metallic bonding because it is a metal, and there is strong electrostatic forces between sodium atom and the electrons because there are charges. So what we're doing is we're breaking this sodium atom off, and we're making it a gas. We're breaking this sodium atom and making it a gas. So we are atomizing the element. And how many moles of the atom do we need? 1 mole. So it can even be for chlorine, where if you have half moles of chlorine diatomic molecule in gaseous state, you're going to get 1 mole of chlorine gas. Now you may ask, chlorine is already in a gaseous state. So what are we actually transforming, or what is the enthalpy change? So basically, don't get confused by the half moles. It doesn't mean that it is one chlorine atom. It basically means half moles of the diatomic chlorine molecule. It's not one atom. So what you're basically doing is breaking the molecule up and making one chlorine atom. So again, the definition is enthalpy change of atomization is the enthalpy change when 1 mole of gaseous atom is formed from its element under standard conditions. So you're going to see this being mentioned quite a bit, which is standard conditions. What does this mean? These are the conditions where 298 Kelvin is the temperature and 101 kilopascals is the pressure. You should remember this because in a lot of calculations, you might be required to use these values. Okay, so that is enthalpy change of atomization. Next up, we have lattice energy. Now, this is a new term. We are not used to the term lattice energy. So what is lattice energy? It is the enthalpy change when 1 mole of an ionic compound is formed from its gaseous ions under standard conditions. So there may be covalent lattice or ionic lattice, but that's not what we're concerned about. The main idea is, let's say this. Let's take this example. What are we trying to form? We are forming an ionic compound. How many moles? 1 mole of ionic compound. So we are forming 1 mole of NaCl. For example, we are forming 1 mole of NaCl, which is an ionic compound. And for doing so, what should our reactants be? In what states should our reactants be? For one thing, they should be ionic. They should be in their ionic states. For example, you don't take sodium atom, you take the sodium ion. You don't take the chlorine atom, you take the chlorine ion, the negative chlorine ion. The second condition is they need to be atomized or in gaseous state. Gaseous state. These are the two conditions for the reactants. So what are you doing? You're first of all, you atomize the element and then you bring in the charges. So you're basically taking the sodium atom, atomizing it, making it a gaseous atom, then you're making it an ion. You're taking an electron out and making it positive sodium ion. So for this structure to be formed, NaCl, the reactant should be in their ionic state and should be in the gaseous state as well. So for both Na and Cl, they are a gas and they are an ion. So again, lattice energy is the energy released when 1 mole of an ionic compound is formed from its gaseous ions under standard conditions. Again, what are the standard conditions? This. So enthalpy change of lattice energy, if I ask you, should it be endothermic or exothermic? You may take some time to figure it out. So let's say, again, for the same example, we're taking the sodium ion and the chlorine ion. We're adding those two up and forming a lattice structure. So for forming this lattice structure, what are we doing? We're creating bonds. We're creating forces of attraction between the ions and we are forming a lattice structure. Remember, formation is always exothermic. So lattice energy, the value for lattice energy is always going to be negative. Why? Because forming bonds are always going to be exothermic. You're going to release energy when you're forming the bonds. Now, why is it that forming bonds are exothermic? Why is forming a bond exo? Basically, whenever there is any sort of attraction, it is going to be exothermic. between the sodium positive ion and chlorine negative ion, is there going to be an attraction? Obviously. Why? Because there is a positive charge and there is a negative charge. They are opposite charges. As a result, they're going to be attracted. Whenever there are attractive forces, it is going to be exothermic. It is going to be exothermic and energy is going to be released. So, what do we know? Whenever there is forming of bonds, for example, in this case, we are forming a lattice structure, energy is going to be released and it's going to be exothermic. Now, for the sake of explaining, I've broken it down into two parts. One is lattice enthalpy of formation. The other is lattice enthalpy of dissociation. What is dissociation? It is basically when you take the ion or ionic compound in the lattice structure actually, and you dissociate it. You may add it to water or any solvent, and you're dissociating the ionic compound and reversing the process basically. You're creating the ions, the sodium ion and the gaseous chlorine ion. Both of them are supposed to be gases because they were initially ionic and atomized. So you're basically, in dissociation, you're reversing the process. So in this case, what is supposed to happen? What is supposed to happen? It is supposed to be endothermic, because in the reverse reaction, you're breaking the bond. You're breaking the bond. As a result, you're getting two separate ions. So, for question papers, when you're going to answer the questions, they're never going to expect you to mention dissociation, or they're not going to expect you to write it's an endothermic process, because this is not actually the definition of lattice energy. Lattice energy actually means the energy released when the lattice structure is formed. They don't include the energy required for an endothermic process, which is breaking down the ionic structure. So this is not a part of the definition. This is just for the sake of explaining, because in a lot of questions, you may be asked to find the lattice energy, but you will be given the ionic compound and you will have to break it down into the separate ions, and then you would be getting a positive value. Why? Because breaking is an endothermic process. So for that case, you may get a positive value, but by definition, lattice energy should always have a negative value, because by definition, lattice energy is an exothermic process by definition. So lattice energy by definition talks about forming of the lattice structure, which is why by definition it's an exothermic process. So when you're supposed to define lattice energy, what do you write? Lattice energy is the enthalpy change or heat released when 1 mole of an ionic compound is formed from its gaseous ions under standard conditions. So what are you forming? Again, the lattice structure, the ionic compound from the gaseous ions, the gaseous positive ion and the gaseous negative ion. So that's basically the lattice energy. Okay. If, let's say, the lattice energy, the value of lattice energy for one is -700 and the other is -400. Let's say for lattice structure A, the lattice energy is -700 kilojoule per mole. And for B, let's say it is -400 kJ per mole. Now, if the value is larger, it means that the ionic compound is much more stable compared to the gaseous ions. What does this mean? So, for let's say NaCl, if NaCl has negative 700 kJ per mole of energy being released to form NaCl, that means NaCl is far more stable than the ions, than the reacting ions. Whereas if B was another compound, let's say potassium bromide, for potassium bromide, if the value is negative 400 kilojoule per mole to form potassium bromide, in that case, the separate ions, the reactants, gaseous potassium ion and the gaseous bromide ion are going to be far less stable compared to the compound KBr, potassium bromide. So, if potassium plus Br minus, both are gases, and they form KBr solid, if these are the products, and it is releasing, let's say, 400 kilojoules per mole, we know that this is less stable than NaCl. Why? Because there is a larger amount of energy being released when NaCl was formed, meaning stronger bonds were formed for NaCl. Since greater amounts of energy were released, that means that the attractive forces between this and this were larger. As a result, the bond formed is also much stronger, which is why NaCl is more stable. For potassium bromide, the attractive forces, let's say, are comparatively weaker. As a result, what happened? Potassium bromide is comparatively a less stable compound. Even in comparison to its separate ions. Why? Because for NaCl, these are the separate ions, sodium ions and chloride ions are not stable at all. They have great attractive forces between themselves. So they're not stable at all. However, when they form the NaCl bond, they're comparatively much more stable. Whereas for potassium bromide, the attractive forces are not that strong. So compared to Na and Cl minus, potassium and bromide ions are a bit more stable. Even as ions, they are a bit more stable because the attractive forces are not that strong. So the compound they form are also, as a result, a bit less stable compared to NaCl. So the summary is, since there were greater attractive forces between sodium and chloride ions, a much more stable compound was formed, NaCl. Since the forces of attraction between potassium and bromide were weaker, a less stable compound, KBr, was formed. Okay, next up we have factors affecting lattice energy. So, in general, there are two main factors that affect lattice energy. One is the charge of the ions or the reactants, and the other is the radius of the ions. So remember, I was talking about potassium bromide and NaCl. I mentioned attractive forces between potassium and bromide ions, and I also mentioned the attractive forces between sodium and chloride ions. So those attractive forces are affected by, one, the charge, which is more important, and the radius, which is a bit less important. Why? I'll explain that as well. So the attractive forces between the ions are affected by the charge and radius. So what is happening? More stable compound formed if the attractive forces are stronger. When will the attractive forces be stronger? If the charge is high or is higher, and if radius is smaller, so that charge density is greater. So this is basically the summary, and I'll right now explain what this all means. You can note this down. This is basically the summary of why you're considering the attractive forces, and if you're considering the attractive forces, why are the factors important and how do the factors affect the attractive forces. So basically, there are two factors affecting the lattice energy. I've mentioned the charge of the ions and the radius of the ions. How does the charge affect? Let's say you have two, NaCl and MgO. For NaCl, what do you have? A +1 charge and a -1 charge. For MgO, magnesium oxide, what do you have? A +2 charge and a -2 charge. What will that result in? For MgO, the electrostatic forces of attraction would be much higher. Why? Because the charges are far greater. +2, -2. They're going to be attracted much more stronger. In a much stronger manner. So, the lattice energy will be greater. Why will the lattice energy be greater? Because the attractive forces were really high. As a result, more energy will be released. If more energy is released, that means from this, we know if more energy was released, the ionic compound formed will be much more stable. So MgO should be much more stable compared to NaCl. So this is how charge effect. If the charge is even greater, that's even better, because the attractive forces are going to be much higher and it's going to release more energy, giving you a much more stable compound, much more stable ionic compound. The second factor is the radius. How does the radius affect? We have two examples. One is with cesium and fluoride ion, and the other is potassium and fluoride ion. So let's say we're keeping the same halide, but what are we changing? The radius of the positive ion. Now, how does that affect? For potassium fluoride, you can see that the radius of potassium is much smaller compared to cesium. What will that result in? Potassium bromide, for that reason, will have greater charge density, because both cesium and potassium have a +1 charge. But the good thing with potassium is there is a smaller area for that +1 charge to be distributed in. Whereas compared to cesium, the +1 charge is supposed to be spread out across a larger area. Therefore, the charge density is going to be less. CD means charge density. I'm just writing in short form. So, for potassium, charge density is supposed to be higher. So, stronger forces of attraction as ions are closer together and the charge density is higher. So, there is another factor, which is since the nucleus of potassium is closer, the attractive forces between the electrons, the bonding electrons or the orbital electrons are much stronger. So it can attract and pull the two atoms closer in a much stronger manner. Since the nucleus is far more closer to the valence shell. Compared to cesium, the nucleus is far away, so it's harder to attract the outer orbiting electrons. As a result, it cannot keep the cesium fluoride intact, or it cannot keep it in a stable manner. The compound is far weaker compared to potassium fluoride, where, for one thing, the charge density is higher and the nucleus are closer. The distance between the nucleus and the outer shell is smaller. As a result, it has a greater pulling force. So this is why with radius, the lattice energy gets affected. If the charge density is higher, then the forces of attraction will be higher, because the overall charge, considering the charge density, is going to be higher. So it pulls the ions together, and the forces of attraction are much higher. So the energy released is going to be far greater. So as a result, more energy is released, therefore affecting the lattice energy in general. So there are two factors again, the charge and the radius. How does the charge affect? Greater attractive forces. How does the radius affect? Increasing the charge density. In return, again doing the same thing, which is increasing the attractive forces. So both are, in a way, doing the same thing. In proportions, if you increase the charge, amount of lattice energy increases. If you increase the charge density, amount of lattice energy increases. Fair enough. Next up, we have ionization energy. We have already studied this in AS, but again, to revise it, the definition is amount of energy required to remove 1 mole of, meaning 1 electron, from 1 mole of gaseous atoms of an element to form 1 mole of gaseous ions. So what are you doing? You're taking, let's say, sodium atom. You're taking a gaseous sodium atom, and you are releasing 1 electron, or taking away 1 electron, and leaving a gaseous positive sodium ion. So for ionization energy to happen, what do you need? A gaseous atom. How do you get a gaseous atom? If you remember, from atomization. So for the enthalpy change, for ionization energy, you need the element to go through the enthalpy change of atomization. If the element or the metal you're using is not atomized, or it is not in the gaseous atom form, you cannot carry out the process of extracting 1 electron, or you will not get the ionization energy. You cannot extract the electron until and unless it is a gaseous atom or metal atom, because for basically cations, you're taking away the electrons for metals. So what do you need for ionization energy? Your condition is you need to make sure that it has gone through the process of being a gaseous atom, right? So that is ionization energy. Turning a gaseous atom into a gaseous ion by taking away 1 electron. Fair enough. Next, we have again a new term, which is electron affinity. What is electron affinity? Basically the opposite of ionization energy. In ionization energy, what do? We take away an electron. And what process is that? Endothermic. Why? Because you're breaking a bond. You're breaking a bond between the electron and the atom. So what happens? You are giving in energy to break that bond. As a result, it is an endothermic process. Now for electron affinity, you are giving an electron. You are giving an electron. So the first electron affinity is defined by the enthalpy change when 1 mole of electron is added to 1 mole of gaseous atoms. Again, gaseous atoms. You cannot carry out the process of electron affinity or giving an electron without turning the non-metal into a gaseous atom. So if you want to add an electron to chlorine, you have to turn it into a gaseous atom, which is Cl gas. Cl, this Cl gas. Other than doing that, you cannot add the electron to the diatomic molecule of chlorine. So you have to atomize it. So after you have atomized it, you can add the electron and form the chloride ion. Okay. So again, it is the enthalpy change when 1 mole of electron is added to 1 mole of gaseous atoms to form 1 mole of gaseous ions, each with a single negative charge under standard condition. Under standard conditions. So this is called first electron affinity. First EA, electron affinity. If you want to add another electron, you can do that as well. And it will be called the second electron affinity. And that's a different conversation entirely. And I'll talk about that. So what could have a second electron affinity? One example is oxygen. It could also be sulfur. So they would have the second electron affinity. Now, let me clear out one thing. First electron affinity is almost always an exothermic process. You could already guess that since I've already mentioned electron affinity is the opposite of ionization energy. So if this is endo, this should be exo. But why is it actually exo? Why is it an exothermic process? Let's draw the atom for chlorine. Let's say Cl. This is the shell. And you have all 7 electrons. And what are you doing to the chlorine atom? You're adding an electron. If you are adding an electron, what are you doing? You're forming a bond. You're forming a bond between the chlorine atom and the electron. What does that do? That is supposed to release energy. Forming is always going to release energy. Now, there is another thing. If it is forming the bond, there is some sort of attractive forces between the atom and the electron. So just for first electron affinity, the positive charge in the nucleus of chlorine, can successfully attract the electron and form the bond. The nucleus has a positive charge, so it can attract the first electron and put it here and form the bond. As a result, since there were attractive forces, it could attract the electron and form the bond. So first electron affinity is always exothermic. Alright. Now, there's one example for first electron affinity where you're taking a gaseous chlorine atom, you're adding an electron and forming a chloride ion. Okay. Now here is the tricky part. The first electron affinity is always exothermic. However, the successive electron affinities, or the second, third, fourth, and onwards, are going to be an endothermic process. Why is that the case? Let's look into that. The second electron affinity is an endothermic process, as the incoming electrons are coming to an already negative ion. Once you add one electron to, let's say, an oxygen atom, you're already making that a negative ion. So if you make that a negative ion, it's going to be really hard to put in or push in another electron. Since this is a negative ion having a net negative charge, the electron has a net negative charge, they are not going to attract each other. So there are no more any sort of attractive forces between the two. What does that result in? That results in repulsive forces between the two. Now, to overcome those repulsive forces, you need to give in energy. You need to give in energy so that the electron and the ion can overcome those repulsive forces and form the bond. So you have to give in energy to form that bond. Now, we can deduce from this, if there are repulsive forces, it is going to be an endothermic process. Okay, great. So, again, the second electron affinity is endothermic, as the incoming electrons are coming to an already negative ion, since there is repulsion. So to overcome the repulsive forces, energy is absorbed. So since for the successive electron affinities after the first one, there are repulsive forces, you have to overcome that, and to overcome that, you have to give in energy, where it becomes an endothermic process, which is why the successive electron affinities are going to be endothermic. Okay. Next we have factors affecting electron affinity. Okay, so for electron affinity, the nuclear charges are a factor, since if the nuclear charge is stronger or greater, there are greater number of protons, it can have a greater pulling force, since if there is an electron outside, if there are greater number of protons, it can attract that roaming electron. It will attract that electron and form a bond. So the greater the nuclear charge, or the greater the number of protons, the better it is, since it can pull the electron. And the attractive forces are going to be much stronger due to the greater amount of nuclear charge or positive charge. Since the charge is greater, the attractive forces are going to be greater and form a bond and take in the electron and form a bond. Okay, it's not basically forming a bond. You're taking the electron and forming an ion. So it's easier to form the negative ion if you have greater nuclear charge. Alright, so the next factor is distance. Greater the distance between nucleus and valence shell, weaker force of attraction, obviously, because the further you move away from the nucleus, the less pulling force and the less energy the nucleus will have to pull an outside electron. If you move further away from the nucleus will have less amount of force on that electron. Why? Because there is greater amount of distance. If you put a magnet beside you and you try to attract a metal, if you put that metal near the magnet, it can pull the metal easily. If you put the metal outside a certain range, it's harder for the magnet to attract that metal, right? Similarly, if the distance between the nucleus and the valence shell is really large, it's harder for the nucleus to attract the electron and form an ion. This third factor is shielding. It's similar to the second factor, but it talks about the middle electrons or the middle shells, the first shell, the second quantum shell. So it's talking about shielding the repulsive forces caused by the first shell electrons and the second shell electrons. So they're going to push the electron away and not let it enter the valence shell and form an ion. Why? Because both of those have a similar charge or the same charge. The electrons in the subshell or the first 1, 2, or 3 quantum shells are going to push the electron away since they have the same charge, and there is going to be a greater amount of repulsion. So if you have a lot of shells, there is going to be greater amount of shielding, and it's going to be much harder to form a negative ion or to pull the electron. Alright, so the greater number of shells, greater shielding. As a result, weaker forces of attraction. Alright, these are the factors of electron affinity. If you increase the nuclear charge, the net charge of the atom increases, the net positive charge of the atom increases, and it is much easier to attract the electron. And the energy released will also increase. Since the attractive forces are greater, the energy released will increase if the nuclear charge is greater. Second, we talked about distance. If you have greater distance between the nucleus and valence shell, the power of the nucleus to attract the electron is going to decrease. As a result, the attractive forces will decrease, so the energy released will decrease. The energy release will decrease since the attractive forces are much lower now due to the greater distance. Shielding, if you have greater shielding, you're going to have greater repulsion. As a result, it's going to be harder to attract the electron, and the attractive forces will decrease. As a result, the energy released are going to decrease. Next up, we have trends in electron affinity of group 16 and 17. So basically, electron affinity applies for non-metals. So we're talking about group 16 and 17. Okay, electron affinity of non-metals are more exothermic across a period as the nuclear charge increases. So if you go from the left side to the right side, it's going to be more exothermic. Granted, you're in the same period or you're in the same row, because if you're moving from the left side to the right side, the number of protons are increasing. So the nuclear charge is increasing. But the shielding does not increase since the number of shells are still the same. So if you, let's say, compare sulfur and chlorine, the number of shells are still the same, but chlorine has a greater nuclear charge, which is why it can have greater attractive forces and pull the electrons easily, which is why the energy released is going to be greater compared to sulfur. All right. Next point, the electron affinity generally becomes less exothermic going down the group. Okay, so as you go down the group, obviously, the shielding increases or the number of shells increase. So if the number of shells increase, there is going to be greater shielding or there is going to be greater repulsion. As a result, the attractive forces will decrease. If the attractive forces decrease, less energy will be released. Okay. And I already talked about this. And I already talked about this. Now, let's talk about the red asterisk. Now, in the second point, we say that electron affinity generally becomes less exothermic as you go down the group. Why? Due to shielding, due to greater distance from the nucleus to the valence shell. So, in that case, shouldn't oxygen and fluorine release the maximum amount of energy? Because the distance between the nucleus and the outermost shell is the least, plus the number of shells are the least as well. So shouldn't they attract the electrons easily and release more energy? However, that's not the case, as we can see, because let's say for group 16, oxygen is only releasing 141 kilojoules of energy, whereas sulfur is releasing 200 kilojoules. Now, after sulfur, you can see it's a decreasing trend from 200 to 195 to 190. But if this trend was supposed to be maintained, oxygen should have had a higher energy release, higher amount of energy release. So it should have been around 225 or 250, but it is less than 200 because it's releasing less energy. Why is that the case? Because both oxygen and fluorine, they're really small compared to sulfur, selenium, and chlorine or bromine. Oxygen and fluorine atoms are much smaller. As a result, the electrons are far more crowded in a way. The charge density or the negative charge density is far greater. So, since the negative charge density is greater, the attractive forces decrease. It cannot attract the electrons as strong as it should have been able to. Why? Because for oxygen, let's say, it has 6 electrons, right? So 1, 2, 3, 4, 5, 6. Now, these electrons are far more crowded and placed in a small area, which is why, since these electrons are in a smaller area, the density of these charges are greater. The density of these negative charge is greater. If the charge is greater, the density is greater and the charge density is greater as a result, the repulsive forces increase. Why? Because these are electrons. And these electrons, this atom is supposed to attract this electron. And if the negative density is high and it is supposed to attract a negative charge, wouldn't there be repulsive forces? There will be a lot of repulsion, and due to this repulsion, it is harder to attract the electron, since the attractive forces have decreased, and now there is repulsive forces. But that is not enough to make it an endothermic process, because the atom doesn't have a negative charge. It has greater negative charge density, but that is not the same as having a negative charge. Since it has greater negative charge density, it is harder for it to attract the electron, but it is not impossible. Okay, so again, both fluorine atoms and oxygen atoms have a really small atomic radius, meaning that the electron density or the charge density is much higher. There is also more repulsion between the electron in these atoms and incoming electrons. As a result, of the repulsive forces, it gets less exothermic. So, yeah, in summary, as the charge density has increased, it's harder for it to attract the electron because there are repulsive forces. All right. So, enthalpy change of formation. This is something we have already learned about in AS. So what is enthalpy change of formation? It is where 1 mole of a compound is formed from its respective elements under standard conditions. So the elements, the reactants, should be in the normal condition. Let's say sodium, you're forming sodium chloride. Sodium should be in solid state and chlorine should be in gaseous state. And that should allow you to form 1 mole of the compound. It can be any compound. All right. So you're turning the elements, you're reacting the elements and forming 1 mole of compound. By the way, enthalpy change of formation can be either endothermic or exothermic, because let's say you're forming ammonia. I don't know if ammonia is an exothermic process or endothermic, but let's say it's an endothermic process. Let's say it's an endothermic process. I don't know if it really is. But what happens is you're breaking N2 bonds and H2 bonds and forming NH3. Right? So you're taking you're taking 1.5 moles of H2 and half moles of N2 and forming what? You're forming NH3. Now look at this. You're breaking the diatomic molecules. And what do we know about breaking bonds? Endo. So there is an endothermic process. And this forming NH3 is exo. So you don't know if the value of endothermic process is going to be greater or the value of exothermic process is going to be greater. You don't know that. The endothermic process might have a greater value. As a result, the net energy change might be positive. Positive kJ per mole. It might be if in the endothermic process greater amount of energy was required, then it might give you a net positive enthalpy change, making it an endothermic process. So enthalpy change of formation may be positive or negative, meaning it can be exothermic or endothermic. Okay, a few examples are between sodium and chlorine, and the other is for forming methane. Alright, so yeah, as I was saying, the final compounds can be either ionic or covalent. It can be covalent or ionic. So you're reacting sodium with half moles of chlorine, and forming NaCl. Similarly, you're reacting C with 2 moles of H2 and forming methane. Now there is an interesting exercise. So there are 5 forms of enthalpy changes, and you have to guess if it's exothermic, endothermic, or both. For lattice energy, what do we know about lattice energy? You're reacting gaseous ions, separate gaseous ions, and forming a lattice structure. So what is it supposed to be? Logically, it's supposed to be exothermic. So if it's going to be exothermic, let's take the exothermic. Okay, next we have electron affinity. What is electron affinity? You're basically adding one electron to a gaseous atom. So if you're adding an electron to a gaseous atom, what is happening? You're forming a bond. But then again, the successive electron affinities, there may be repulsion between the already negative ion and the extra electron or the second electron. So in that case, you have to give energy to form that bond. So if there is repulsion and you're forming a bond, it becomes an endothermic process because you have to overcome that repulsion. Which is why electron affinity can be both exo or endo. So we're going to give both. Ionization energy. Now, similar to electron affinity, it doesn't have any sort of, unlike electron affinity, it doesn't have any sort of exception. All ionization energies, all the successive ionization energies are always what? Exothermic. Are always exothermic. No, it's not exothermic, it's endothermic. Are always endothermic. Why? Why is it endothermic? Because you are breaking off an electron. You're breaking off an electron from the atom. So, what are you doing? You're giving energy. You're giving energy to break the bond. Which is why ionization energy is an endothermic process. Atomization. For enthalpy change of atomization. What's happening in atomization? You're taking, let's say, a solid sodium atom and turning it into a gas. A separate sodium atom in gaseous state. What's happening then? You're breaking the bond. You're breaking the, let's say in this case, the electrostatic forces and making it a gaseous atom. Not ion, gaseous atom. So you're breaking bonds. As a result, it is, endothermic. Formation. As I've already mentioned, formation can be both exo or endo, which is why you give both. Alright, so that is it for this video. I'll continue to do the other topics and the other parts in the next video. There is a bit left for enthalpy change, basically the Born-Haber cycle, which is the most important part. The Born-Haber cycle is basically why we are getting used to all these new terms. So yeah, see you in the next video.